IIIT Allahabad, India, MS in Electrical Engineering, Intelligent Systems, Robotics and Control, and PhD in Electrical Engineering, Intelligent Systems, Robotic and Control from University of California, San Diego, USA. Dr. Siddharth has a lot of awards, and his awards have started since his bachelor's degree, I believe. Because if I read out, it takes a long time about the fellowship honors and awards. I'll just brief out just to inspire all the participants. Dr. Siddharth has been awarded with many awards from Indian Institute of Technology, first prize in electronic quiz competition, till very recently from Facebook Reality Labs research grants in 2019. To University of California Chancellor's Research Excellence Scholarship in 2018, Kavli Institute of Brain and Mind Innovative Research Grant in 2018, and many more. Very interesting and inspiring about Dr. Siddharth is patents been awarded. 4 patents has been awarded, published and awarded by Dr. Siddharth. The patents goes like this: biosensing and eye tracking system. The second one is on wearable multimodal biosensing system. The third one is on very interesting emotion evaluation. The fourth patent is a method and apparatus for similarity detection of documents based on contents including text, tables, flowcharts, and equations. Very interesting research in progress by Dr. Siddharth and his team goes like this: working towards publishing a book, Founding Generations, Democracy's Origin and Parallels in America and India. Very, very interesting on the founding fathers and origins of democracy in India and United States of America. The second research work in progress is on assessing the relationship between emotion elicitation and detection from the biosensing perspective. The third research still in progress is on conducting experiments to modulate games in real time by utilizing affective feedback. And there are many more such interesting factors about Siddharth, and I hope his talk today will deliver all these contents. Thank you, Dr. Siddharth, and here is the mic for you.
Thank you, Professor, for your generous introduction. Thank you, everyone, for tuning in today. Should I start?
Yes, sir, please.
Share my screen. Hope you can all see it.
Yes, sir.
Okay, so thank you everyone once again for attending this. Now, the topic of my presentation today is utilizing cost-effective multimodal biosensing systems toward real-world effective computing scenarios. Most of this work I have done in the past 5 years through my PhD doctoral degree, and also through the internships that I did in Facebook Reality Labs, and some work has been done at Microsoft. So it's a blend of both industry and academia in the United States. Now, if you focus on the title of my talk, I have highlighted a word in green, cost effective here. This I have deliberately inserted today. Now, I have inserted this because I wanted to highlight here that all the research that I have done, this could have as well been done in any institute because it does not need like hundreds of thousands of dollars or anything. I mean, if the university in the United States, they don't have to pay me stipend and all the infrastructure that I used were basically computers, GPUs, and some biosensing systems, which I'm sure most IITs and other engineering colleges in India have these days. So all the work can be done in any engineering institute in India. I would definitely say that. That's why I was cited this word here, cost effective today. The other words are these 4 highlighted words: multimodal, biosensing, real world, and effective computing. So about these 4 words, I will talk briefly. This work was majorly done in these labs in University of California, San Diego. These were the labs that I was associated with during my doctoral studies. So let me start in a little bit unusual way from using this type of format, 5 Ws and 1 H. So what happens is in journalism, if a reporter goes to cover a story, so the reporter goes and covers a news story, and the reporter comes back to the editor saying that, hey, I have covered the story that I wanted to cover. Should we publish it now in the newspaper next day or on the television? Should we show it? So the editor usually asks these 6 questions, 5 Ws and 1 H. So who did you interview? Where did you go? What did you do? Why did it happen? About the event? When did the event happen? And how did it happen? So using this format to answer everything in my PhD research, let's ask these questions. So who is very easy to answer here? I did the work with my collaborators, and most of the work was done at UC San Diego, while some of it was done during my internships in Facebook Reality Labs. Now, the other 4 questions, let's use these questions to come back to the topic of the discussion, and let me try to answer what these 4 words mean. So what is affective computing? Why use biosensing for affective computing? When are multimodal systems advantageous, and how to apply these multimodal systems toward real world applications? So these are the 4 topics around which my talk will be based today. So let's dive into them one by one. What exactly is this thing called affective computing? So affective computing is the study and development of systems and devices that can recognize, interpret, process, and simulate human affects, that is feeling, emotion, or mood. Okay. It is a very broad field. It has inside it computer science as well as psychology as well as cognitive science. Affective computing is actually a newer research field as compared to the study of emotions. Why do I say that? Because probably as long as humans have been self-aware, they have wondered about the origin, essence, and utility of emotions. In Western, especially Greek philosophy, emotions, or in Latin, emovua, were considered as playing a destructive role in decision making. While in the Asian philosophy, in the Eastern, especially Buddhist philosophy, emotions or bhav were considered as a hindrance preventing liberation from suffering. So emotions have been thought about and debated as long as humans have been self-aware, as long as philosophy has been invented by human beings. But such an obsession with emotions has naturally led to much research in studying their origins and classifying them into various categories, because you cannot just study emotions without classifying them into different sort of categories. For centuries, 2 methods have been predominantly used to this end. The first have been to receive human feedback. So you ask the person, how are you feeling? Constantly keep on asking the person many times a day. Or if you go to a psychologist, the psychologist asks you, how are you feeling today? How were you feeling yesterday? How were you feeling 1 month back? How have been your emotions in the past 1 week? So this has been the easiest, right? Receiving human feedback. Just ask the person what is your emotion now or has been throughout the day or whatever. And the second has been to recognize the facial expressions. So you use either a camera, or even if you don't want to use a camera, I mean, human beings do it all the time. Whenever we encounter a person, we recognize or try to recognize their facial expressions using our own eyes, right? So we always, all the time, use computer vision to recognize the other person's emotions. But with developments in electronics and computing in the past half century, it has now become possible for the first time in human history to do this in an automated manner. So you don't have to keep on asking the person, and you don't have to like do it yourself, recognizing through your own eyes or your brain. You can actually do this in an automated manner. You can classify emotions of a person automatically. Now, these developments have emerged as a significant component of effective computing. If you go to the IEEE transactions on effective computing, you will see most of the research papers, even now, are about classifying different emotions. So, however, above 2 methods that I just showed you, receiving human feedback and recognizing facial expressions, they can be easily implemented in a system by a joystick and a camera, right? You can just give a person a joystick in hand, and based on what the emotion is at that point, the person can manipulate the joystick to tell you. And for recognizing facial expression, you can just put a camera, right? You can just use a camera and some computer vision to figure out what the person's emotion is. So why use biosensing? That's the second part here. If you can already do this using a joystick or a camera, why exactly should we use biosensing? So suppose you have come back home and you are very tired, you are exhausted after the day's work, and you just want to crash down, and you are not looking forward to your evening. And let's say somewhere in your home or somewhere on your body, there's an intelligent assistant, and it detects, I detect you are upset. This could help. And the intelligent assistant, it plays your favorite song and turns on the television. And suddenly you are more rejoiceful because it is helping you in calming down. It is helping you in rejuvenating in the evening. Why did this happen? Because the intelligent assistant somehow it got to detect through some sensors around you in the room or on your body that you are not feeling very well right now. You're kind of upset. So to do something like this, we need biosensing because it is impossible to continuously receive user feedback. You cannot keep on asking the person every single hour or every single 15 minutes that, hey, what is your emotion? So you need something in which you can get an automated information. It is impossible to always use good illumination. So you cannot always have good illumination on your face. So you cannot always use a camera, right? You may be walking outside, or you may be in your room at different points of the day when the illumination is different, or you may be in different rooms. So you cannot always use a camera to see a person's face and detect his or her emotion. And then it is impractical to use ego camera everywhere. You cannot always put a camera in front of the person, especially when you are walking or you're doing some physical activity. And then camera uses raise issues concerning privacy because it will not only record you, it will also record your surroundings and perhaps also people around you. So there's the privacy concern. And I believe biosensing may provide the solution because if you are wearing something like a smartwatch, like an Apple Watch or a Fitbit or something, and then you want to measure your different bodily parameters. So that's exactly what I mean by biosensing here. It may provide the solution because it is non-intrusive. You are only doing it on your body. You are not, there's no privacy concern with it. It does not depend on external factors like illumination or occlusion, etc., since it is already attached to your body all the time. And it is capable of highly individualized analysis because the parameters that it will record, such as your changes in your heart rate or heart rate variability, changes in how much sweat you are secreting, all these will be highly individualized only for you and only for that environment in which you are in. So if I want to put all my goal with this talk in just one line, I would say we are trying to make a sort of a Fitbit or sort of like an Apple Watch for emotions. Okay. So, and also please feel free to ask any questions at any point if anyone has any question. So the goal here is to make a smartwatch or a small sort of device somewhere on your body, which can detect and classify your emotions in real time in a very non-intrusive manner, which does not raise issues of privacy. So what should be the goals of such a biosensing system? So the first one is, of course, to detect and monitor the affective states, which is detect and monitor human emotions. Second would be to infer these affective states, that is human emotions, using a minimal number and most comfortable sensor. You don't want to put the person in a whole fMRI machine. You want to have detect the emotions in the minimal number and the most comfortable sensors. You have to infer the context in the real world scenarios that, okay, if I detect that the person is happy, what's the context here? Why is the person happy? So you have to know about the real world scenario, about the surroundings of the person. And based of the information from all of this, you want to make some recommendations to the person or to take some action. For example, if you detect for long that the person is upset, you might want to recommend to the person to listen to a song or just to go outside, take a walk to refresh yourself. So what kind of recommendations should the system make? And then the fifth, which is the hardest of these all, is to keep on doing this continuously throughout the day. Doesn't matter what the illumination, it doesn't matter what the condition is, doesn't matter what your surrounding is and everything. So for most of my PhD thesis, I focused on the first 3 points. So these are the 3 points that I will discuss about. Now let's move on to the third part here. When are multi-model systems advantageous? So biosensing systems have been there from a long, long time. You like in hospitals, ECG and EEG, these type of technologies, they go back about almost a century. But until about 10 years ago, these systems used to be bulky. You had to go to a hospital to have your ECG detected, or these eye tracking sort of platforms. You had to put your face on a chin rest, and the EEG was also very bulky. So until about 10 years ago, all these systems used to be very bulky. Then until then, about 5 years ago, these systems started coming in a very compact form factor. So now you could do ECG just by wearing a belt around your chest. You don't need all these wires coming out of these amplifiers. You can do eye tracking using just eyeglasses on your head. You can measure EEG using a wearable EEG device like the one shown here. But now is the time that we have compact multi-model biosensing systems. So instead of just one modality, for example, instead of just monitoring your ECG, that is your heart activity, now the single system may be able to measure your heart activity as well as how much sweat you are secreting, which is galvanic skin response, the conductance of your skin. So not just one, but now you can do multiple different modalities in the same system. For example, in this one here, as an example, you can measure your EEG, which is your brain waves, the electrical activity of your brain, as well as you can put a small camera for eye tracking. So multiple modalities in the same system. That's why multi-modal systems. Okay. Now, but there are some challenges in using this. First is they do not provide research grade biosignals usually because they are made for like a consumer platform, not for a research grade platform. They cannot usually be customized as per the experiment's needs. And then the data synchronization among different sensors is cumbersome. Usually you have to buy like one sensor from one company, one from another company, and then you have to figure out how to synchronize the data between them. So to solve these problems, what we developed was our own multi-modal biosensing system. This is the system architecture. So as you can see here, we have a color camera to see the person's world view, that what the person is looking at. We have an infrared camera to for the eye view, so that we know what is it that like how the person's eye is moving. So the infrared camera will point to the person's eye. We have headphones and speaker here if you want to run some experiment. This embedded system which gets all the information for all these different modules, such as the EEG module for the brain activity, the PPG module for the heart activity, and then it transmits all of this data through a Wi-Fi transceiver to your laptop, or you can also store it on a memory card. So this is a system architecture for this multi-modal biosensing system. First, we will talk about this part, the color cameras part, which are being used for eye gaze tracking. So eye trackers have some limitations, those ones that are currently in the market. Either they are non-mobile, that is you may want to put your head on a chin rest, or they can be also be very, very costly. For example, this eye tracker costs about $30,000. So what we developed was, again, we developed this in-house in lab, and this could be done anywhere in the world in just a few, I would say $200, $300 at the max. So we developed a customizable eye gaze headset in which there's a world camera here, as you can see, which is used to record everything from user's perspective. So if you put on these eyeglasses, this camera, using this camera, you can record everything that the person is looking at. There's the infrared based camera to detect the person's pupil, the center of the person's eye. The headset is customizable. You can change the size and those kind of parameters. The both cameras work together at this resolution at 30 frames per second. It's fast and easy to calibrate and can work when the subject is mobile. Because as you can see, you can just wear it and go anywhere. And it can work with the conditions of varying illumination, because using infrared camera here, you are using infrared light to detect the center of your eye, that is the pupil. So this is kind of how the algorithm looks like. So if you are watching this kind of a scene, your eye here is being marked and the center of your eye is being marked here in red color. That is your pupil. And the confidence of the algorithm is comes here. This pink dot here on the screen, this is your gaze. So this dot moves around whenever you look at different points of the screen. So this is your eye gaze. The types of biomarkers that we can extract from this system are eye gaze overlaid on user's worldview. This pink dot, as I said, wherever the person is looking at, you can get this information. You can get information about the pupillometry, which is pupil diameter, fixations, and blinks, because you can just put a computer vision algorithm to detect blinks here when the pupil is not being detected. So you can know when the person is blinking, how much the person is fixating, and the pupil diameter. All of these then you can use to train on emotions, right? Because these type of parameters, you can use machine learning on them to detect somebody's mental state or cognitive state. And then you can also pinpoint the visual stimuli to which the user is reacting. Because, for example, this gaze, the pink dot, if this lands on a flower, you can at that point pinpoint to the person's brain activity and heart activity to know the changes when the person looks at a flower, or when the person looks at a laptop or this painting, and you can then monitor these kind of things over time. Then we move on to the second part of this system, the PPG module. So PPG actually stands for photoplethysmogram. Basically, you send light to your skin, and the way the light penetrates the skin, you try to monitor it. And because your heart is beating all the time and the blood flow is changing all the time at that point of the skin, you get a profile using which you can know your heart rate and heart rate variability. So there are already cardiac systems available in the market. Some of them are difficult and uncomfortable to wear, and they require wet electrodes. So these are, as you can see, not very comfortable to wear, and also they're very intrusive to privacy. Or the other ones, such as the smartwatches one, they have usually have low sampling rate, usually about only 10 hertz. So you cannot calculate heart rate variability. You can calculate heart rate, but not the variability of heart rate, because for that you need a much higher sampling rate. So heart rate variability you need, because for emotion detection, that is a very important parameter. So what we did was we developed our own multimodal biosensing system. Again, very cost effective, cheap. We designed the board ourselves, and then we fabricated it ourselves by hand. And as you can see, using United States quarter coin here, it is very small. So very compact form factor. Now this you can easily wear behind your earlobe. So we made it so small so that you can actually clip it behind your earlobe using a magnetic assembly. Um, Here's a infrared emitter detector, which sends which sends infrared light through your earlobe, and the way the light penetrates or does not penetrate based on your heartbeat activity, we can get a profile of your how the blood is moving inside your earlobe, and that we can use to get your heart rate and heart rate variability. Also, the board has an accelerometer, because using the accelerometer, we can use adaptive noise cancellation, so that when you are walking, we can use the accelerometer to model.
I would also go out.
Sorry. So you can also use the accelerometer for modeling the noise. Okay, as you are walking, you can model the noise of your steps using the accelerometer, so that you can cancel that noise from the PPG. The extractable biomarkers from this are heart rate variability, and head movement and orientation. Now, the third part of this system is the EEG module. EEG, as you may all know, stands for electroencephalogram. It's the brain activity at the human scalp, the electrical potential of the brain. So reliable brain-computer interfaces, they are bulky, as you can see. So many wires are needed, and they generally use wet electrodes and everything. So what we did was we made our own small electrodes. Again, you can see compared to a US quarter coin how small they are, and we fabricated them ourselves in-house. So you can see we ourselves made these lectures made out of silver epoxy, and we ourselves made a filter assembly here to filter out the noise. They're very low cost, so each of these to us costed $2, but if you are making in bulk, they will not even cost a single dollar. Currently, we were using 16 of these electrodes to cover different parts of the brain. Then we were using a very ultra low noise 24-bit analog to digital converter to convert the EEG signal from analog to digital. And all of these electrodes, we used a small copper tape around these so that we can shield it from outside noise by making kind of a Faraday cage around the electrode. So using these electrodes, we can extract the EEG brain activity, which then we can use for multiple secondary applications, such as detecting person's arousal or motor activity or visual evoked potential or speech analysis, etc. Not just this, we can also use some other sensors from the market and integrate them with our system because the software library that we are using is very scalable. So you can use, for example, a motion detection system or a GSR band or any of the other bands from the market and integrate them with our system. This is the heart of our system, the embedded system, which looks like this. So as you can see, again, it is very compact, only about 7.6 centimeter to about like 4.1 centimeter. Um, this is how the system looks like on the right. So the eye camera here, this eye camera looks at the eye of the person and it detects the center of the eye so that using the world camera where the person is looking at, it can overlay the person's gaze. Okay. The PPG sensor here goes behind the earlobe. So just from your earlobe, the PPG sensor detects your heart rate variability. All this embed system comes very neatly in this 3D printed platform here. These are the EEG electrodes. So 16 EEG electrodes right now across the whole human head. The battery is sandwiched here, and then this is the EEG reference. So that's how one version, like the earlier version of our wearable headset looked like. This is how the software from the wearable headset looks like. So in this frame, you can see it detects if there's a face present, then do face detection here, mark the person's face. This is the gaze of the person wearing the headset. So it is being overlaid here in pink color using this human pupil. As you can see, this is marked in red, the center of the eye. So you can know the person's gaze and overlay it here. PPG data is coming here, which is in real time measuring the heart rate, which is currently here 78 beats per minute. And accelerometer data is also being used in real time to remove any noise from this heart data. Now, we also use deep learning to recognize different objects. So as you can see here, detect that this is a person, and then if it is a person, what are the different limbs of the person? Where are they? So what is the posture of the person? So using all this information, what we can know is where exactly you are looking at. So you are looking at somewhere on the screen, and what exactly is this? So you are looking at somewhere on the body of the person, right? You are somewhere looking inside this person bounding box. So you're looking at the person. That's one information we get. And what is happening to your heart activity at that moment and what is happening to your brain activity at that moment. We can get all this information using this headset. So these are again whatever we developed, all the contributions as I already mentioned. So I'll just skip this part. Now to evaluate the system, what we did was we did two different studies. One is where is Waldo and one is playing rock, paper, scissors game. So we used 10 subjects, 13 where is Waldo scenes and 50 rock, paper, scissors trials. And these are real world tasks, but they were a little bit controlled in the sense that we asked the person not to move the headset a lot, not to start like suddenly stand up and start walking so as to not like change the position of the headset and introduce noise. So they're somewhat controlled, but still they are real world in the sense that these are kind of games that we play in real life and you can just sit on a chair and play them. So what is this game? Where is Waldo? This is kind of a puzzle game in which you see this kind of an image in a book and you have to find this character Waldo inside this puzzle. So for example, in this particular image, the Waldo is here. So that's game. Where is Waldo? And we actually had 10 subjects playing this 13 times each. And this is the plot, how much time on average these subjects took. So as you can see, they are neatly divided into three different categories. These people took the highest amount of time on average in finding Waldo, where these people were the fastest. And then what we did was based on how your gaze is moving on the screen to find Waldo, we found the median Euclidean distance of all the fixations. So if you are fixating on different points of the screen to find Waldo, how much is on average, on median average, how much is the distance between successive fixations? So are you trying to suddenly move to different corners of the screen while finding Waldo? Or are you trying to go in a small pattern? So looking at a small part of the screen, then moving to another small part of the screen. And based on this, what we found was there were again three different groups based on this median Euclidean distance. for finding where is Waldo, just like we found there are three different groups on average which take different amounts of time in finding where is Waldo. What this means is those people who try to find Waldo in a small part of the image, as you can see on the left one here, these people find the Waldo in the least amount of time. So these people are the most efficient. Whereas those people who suddenly start looking for Waldo by randomly gazing everywhere on the whole uh, image, they take the most amount of time. So next time you play the game, you know that you should start in a small part of the image and then move on, build over it to other parts of the image, rather than suddenly going across all the whole of the image to start finding Waldo. Now, this type of an insight would not have been possible if we were not using a multi-model system, right? Because you need these two different cameras and you need all these type of apparatus. Only then you will be able to get these type of insights. Just using one type of sensor, you would not have got this insight. That's why this type of evaluation is multi-model. We also use the brain data from this. So when you're trying to find the character Waldo, you will also have many wrong fixations, right? You will find, oh, this is Waldo, but oh, no, this was not Waldo, I was wrong. Then this type of false fixations, how does that impact your brain waves? So when we plotted these on average across whole subjects, we can see that for false fixations, we get this type of like ERP response, whereas for the target fixations, the ERP response is different. So target here means Waldo. We can very easily separate this means from your brain activity if your fixation was actually Waldo or it was a wrong fixation. So it reflects in your brain that when it happens that, oh, is this Waldo? No, 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 this is not Waldo versus yes, I found Waldo. We get very different profiles in the brain activity for the two cases, the false fixation case and the Waldo case. Then we move on to the second experiment, which was playing rock, paper, scissors. Again, a very real-time, real-world experiment because this is a game which I guess everyone plays. So rock, paper, scissors is a for those few of you who may not be aware, is a game in which you play using your hands. So this is rock, this is paper, and this is scissor. So it's a two-person game. If I do paper and the other person, if I do scissors and the other person do paper, then I win. But if I do like rock and the other person do paper, then he or she wins because the paper supposedly wraps the rock around. So that's like the game, the rock, paper, scissors game. And here we plot the heart rate variability for lose or win conditions for this game. And as we can see clearly, the heart rate variability shows a correlation for different subjects, though it is not very high. That what will happen to your heart rate variability, how will your heart activity react if you are winning in the game or you are losing in the game. We also used the information from EEG and from again the PPG, which is the heart rate activity, to try to classify if it is was a loss or a draw or a win, or just for two cases if it was a loss or a win. And for both of these cases, we found that the mean accuracy was much higher than the chance accuracy. So just by using your heart activity or your brain activity, or using both as in these columns here, when we use the information from both of them, from PPG as well as EEG, we can actually know if um, you were winning in the game or you were losing in the game or it was a draw with a much higher accuracy than chance accuracy. So the contributions of this part of my talk, we evaluated and designed a sensor platform on practical real-world tasks to demonstrate the advantage of simultaneously using a multi-model biosensing system. It was impossible to garner such fundamental insights into strategies employed by users during such real-world tasks without a multi-model biosensing system. So this is the key here. Without using a multi-model biosensing system, we would have not been able to do such tasks because for this real world task, you need both biosensing systems, not just camera or asking users feedback. And you also need them to be multimodal because you need more insight than just using one type of sensor. Then we move on to the final part of the talk, which is also the longest part. So how to apply everything that I have shown you until now, biosensing, multimodal systems, application of active computing, how to apply them toward real world applications. So we will focus on two real world applications in particular here. The first is consuming multimedia content, and then the second is monitoring driver awareness. Both of them are very, very much real world tasks. The first one, consuming multimedia content, is something we do all the time, which is basically watching movies or watching something on YouTube or watching a TV series, anything. So consuming any type of multimedia content. And then second is monitoring driver awareness. So whenever you are driving a car, how to monitor the awareness of the driver, that if the driver is awake or if the driver is feeling sleepy or if the driver is kind of not, so to say, cognitively very active in driving. So again, I would like to emphasize here, these are two very much real world tasks. So let's focus on these one by one. First, consuming multimedia content. So let me introduce you to this thing called emotion circumflex model. On the x-axis, if you can see on the right image here, on the x-axis is something called valence, whereas on the y-axis is something called arousal. So valence is kind of like your mood, and arousal is how much aroused or how much activated you are. So based on this model given by Russell in 1978, which this is like the most used model for classifying human emotions. So based on this simple model, we can use this to classify any human emotion. For example, if your mood is positive, that is your valence is positive, and your excitement is also high, your arousal is also high, we would know that you are excited or you're delighted, right? You will be somewhere here in the first quadrant. Whereas if your mood is negative, which means you're on the left side here of this plot, and then your arousal is also not very high, so that means you're tired because you're not excited at all, you're not aroused at all, and your mood is also negative, it's not positive. Whereas if your mood is positive while you're not aroused, you're calm. So this on the left is just a more sort of has a higher resolution plot of this plot on the right. This emotion circumflex model we will use to classify a person's emotion. Okay, so we will use these things called valence and arousal to map a person's emotion. Now, consuming multimedia content, how these type of studies are done. So, for example, there's one of these data sets which is very widely used called Mahanov HCI data set, in which you have 27 subjects sitting here, and they're watching 20 short movie clips. Okay, so such as a clip like this one. The data from this data set includes upper body 2D videos, because you have all these cameras around the person, so they are actually capturing the person's upper body. Of course, it includes the human face. You have 32 channel EEG. As you can see on the head here, you have a EEG system to record the brain activity. You have one channel electrocardiogram, ECG. So somewhere on the chest, the person has a ECG for the heart activity. You have a GSR for the galvanic skin response, which basically measures the conductance on the human skin. And then you also have a eye gaze system here to measure the human eye gaze, so how your gaze is moving. And then after watching each of these short videos, which are about 30 seconds to 150 seconds long, the person has to answer these questions. So what was your valence, ranging from 1 to 9? What was your arousal, ranging from 1 to 9? What emotion were you feeling in different classes? What was your happiness level? What was your sadness level? And these type of questions. So we will use valence and arousal from here to classify a person's emotion, because as we saw here, valence and arousal we can use to map any of the human emotions. So this is an example of the multimedia clip. The video here is of a horror movie. So this lady here, who is probably seeing some sort of like ghosts or whatever, as you can see here.
It's not audible. Hello? It's not audible, sir.
So those were two kind of examples. I just cropped them for time purpose, but those are kind of like the example videos that the person were watching. So these type of videos like horror or comedy or like drama, These type of the videos were the videos that the participants were watching, and for each of them, they were rating their valence, their arousal. Now let me just give you a little bit like blast to the past. What about the previous work in this domain? So there have been these 4 data set that have been predominantly used for these type of studies. And if you would focus on these 2 columns here with the arrows, so most of the studies here, they have only used a single modality, right? Predominantly EEG, while only some of them have used multiple modalities like other ones, ECG, EOG, or skin temperature, etc. And even after that, for all these data sets, if you would see, 50% is like the chance accuracy for arousal and valence, and most of them have not gone beyond like 77%. That's like the highest. So in a time of like deep learning, and in a time of when you have so much sophisticated signal processing tools, why is it that this problem has not been solved? Why is it that you are not getting like 99% accuracy even for a 2-class case that was your mood positive or negative for these type of videos or for these type of tasks? The answer is emotions are highly individualistic. For example, for the same video, for example, if we focus here on video ID2, this person here absolutely felt nothing because this person is like neutral, whereas this person here absolutely loved the video because the valence is very high, so very positive mood and very much aroused, so like totally excited. Whereas these people here, these people are very much calm because their valence is high, but their arousal is not that much. Again, let me focus on some other one to illustrate this point. For example, this video ID 11, this person here is calm because again, positive mood, but no arousal. Whereas these people here did not like the video at all because they have negative mood and very aroused in that negative mood. So they just did not like it at all. Whereas people here are kind of neutral because they are near the neutral part here. So emotions are highly individualistic. The way I would find a horror video would be much different than you may find it, right? If I like horror, I may rate the horror video somewhere in this part. Whereas if you completely do not like horror, you will rate it somewhere in this part. So emotions are highly individualistic. That makes it a very hard problem to deal with. And second is there are many discrepancies among the data sets. So some data sets, they use music videos while other use movie clips. Some use a 32 channel EEG system, whereas other use 14 channel systems. So some may record phase, others may not record phase. Some may ask the person to rate on a scale of 1 to 5, other may ask on a scale of 1 to 9. So there's no sort of like industry standard or academia standard in this in these type of studies. So and that's why, because there are discrepancies among data sets, you cannot scale very easily from one data set to the other. To tackle these problems, what we did was, as I will show you in the following slides, we tackled each of the modalities separately. So we tackled the EEG, the brain activity separately, and we extracted conditional entropy features. Now these features are basically the features based on mutual information. So you have all these different sensor pairs. Now, by mutual information, what I mean is if you have information about this part of the brain and this sensor, how much of this sensor's information is correlated with the information from this sensor, and like this you do for all the different pairs of the brain. So that's what mutual information here stands for. So we use mutual information features for all possible pairs of electrodes. Now again, because some of the EEG channels are only 14 channel, you get 91 features, while others are 32 channels, you get 496 features. So I will show you in just a moment how did we tackle these different number of channels. But suffice it to say that these type of features, the mutual information features, they try to map how the brain is reacting across the different regions of the brain, because you find the mutual information across all the pairs of electrodes over the whole brain region. This is how the conditional entropy matrix looks like. So again, you can see for each of the pair of electrodes, you can get this information. Now what we did was we used the theta, alpha, and beta. These are the three power spectrum frequency bands. So these three bands actually capture different sort of brain profiles. For example, alpha band captures if you are awake or not, if you are sleepy, whereas beta band is sort of more related to cognition, to your emotions and all. So these three bands we extracted from, this is just like basic EEG processing. So if you are an EEG guy, you would know this is what you were studying the first week of your class, that these are these three EEG frequency bands, theta, alpha, and beta. But the catch here is what we did was we extracted theta band in the and we then plotted it using only the red channel, then green channel for alpha and blue channel for beta, so RGB. And then based on the scales here, how much is the information in the band, we actually edit them so that we can get a colored image. So the three-channeled image as a colored image here. So red channel plus green channel plus blue channel gives you a colored image, a RGB image. And then this single image now has the information from all of these three bands combined. So now using just one image, you can actually represent all the information in the theta, alpha, and beta bands combined, and then we send this image to a pre-processed, like a pre-trained deep learning network, here a BGG16 network. And when we send this to a pre-trained network, what we did was we used the second to last layer here, 4096 features from them. And then we use these 4096 features for further processing. Now, what this allows us is this. Even if we have 496 features because you have 32 channels, or you have 91 features because you have 14 channels, the image you will always get will be the same, right? Because even if you have 14 channels or 32 channels, you will get the same size of the image. It might have a little bit more resolution if you have 32 channels, but the image size and everything will remain the same. So now you can actually use these type of images and this type of features across all these different data sets, because again, doesn't matter you have a 14 channel EEG headset or a 32 channel EEG headset. So after that EEG processing, let me come to what we did for PPG, which is again photoplethysmogram. So this is PPG, how a PPG wave looks like. So number of red peaks here are your heartbeats. The number of these peaks in the number of seconds, that's your heart rate. What we did was we actually calculated the heart rate variability in time domain, which is how these peaks are varying, how much is the variability of your heart rate. And then we converted this time domain data into frequency domain to make a spectrogram image. And then again, like we did for EEG, we send this whole spectrogram to a deep learning network, a pre-trained one for feature extraction. Exactly the same for we did for GSR. First, we calculated some time domain features based on like first and second order entropy for the GSR signal here. And then we converted the GSR time domain signal into a frequency domain signal so that we can send this image into a deep learning network. Now let's come to the face video analysis. So for face videos, what we did was, if this is an image, first you detect a person's face, then you find the face landmarks. So these are the face landmarks here marked in green color. And then for each of the frame, you find that you like hand code some of these landmarks. So for example, the distance between the eye, horizontal and vertical, the distance between different parts of the lips, horizontal, vertical, and the angles between them. So basically what we are trying to do here is to map how your facial expressions are changing, how are you opening your mouth, how your nose profile is changing, how your eyes are being opened or closed. And using this, we get 30 different features we extract 30 different features using these facial landmarks, which I say as localized points, such as distance, intersections, and angles. And then we normalize these over the face because the distance from the camera may influence it. So we normalize them based on the size of the face on the camera using this width and height of the face. These features, then what we did was we found the mean 95th percentile and standard deviation of these features for the whole video trial. So whenever you're watching a video, we extracted this for the whole video of your face when you're watching any sort of that type of multimedia content. What we also did was we also send these images directly into a deep learning network. So let's just let the deep learning network figure out what are the best features out of these, and then we combine the features. Not only this, so until now, all the features that I showed you, these are the features from the person, right? These are the features from my brain activity, from my heart activity, or from my face. But when I'm watching that type of content on YouTube, we also wanted to get the information from the content itself, that what is the information from the content itself that is influencing my brain or that is influencing my heart activity. So, for example, these are kind of features that producers or directors take into account when they are directing a movie or a commercial or anything. Short duration. So, how much is the short duration? This is a measure of the perceived passage of time. For example, if you are watching, if you're watching sort of to say action movie, then the short duration would be very less because you would cut again from one shot to another shot. Whereas if you're watching a drama, the short duration will be will usually be much more because uh, you might have a shots of 30 seconds or even up to 1 minute, 2 minutes, 3 minutes. The people may shot all of that in just one take. Whereas for an action movie, you cut from one scene to another scene very fast to kind of have like a feeling of excitement in the audience. Visual excitement, again, another feature very important, which has an algorithm which you can use to calculate the arousal arising from the motion in the video. Lighting key, how much is the different amount of lighting in the video? For example, horror movies tend to be rather like black and like gloomy, so lighting key is not that much. Color energy, how much is the saturation or the brightness of the different regions occupying different colors. Other video features were also extracted, such as these called gray level co-occurrence matrix GLCM features. These are basically texture-based features. How are the textures varying in the different images that you are viewing? We also similarly extracted audio-based features. So MFCC features, which are the mel frequency substitute coefficient features, these are very sensitive to how our ears like how our ears perceive the audio. So MFCC features we extracted to know how is the audio changing as per how you are listening to it, loudness of the video, probability that there's a voice in the video, and then some tonal features. So we actually 19 audio features in total like this. This is to give you an example. So for example, this was the video that we were watching earlier. So if in a 15-second segment like this, one video is this one is this kind of a gloomy horror video, and one is this video which is of a weather report. So kind of videos that we watch on YouTube every day. Voice probability for these three, as you can see, are different. The weather news guy is talking all the time, so the voice probability is the highest here. Number of shots, as you can see, Mr. Bean has 4 different shots in these 15 seconds. 1, 2, 3, and 4. Whereas the weather guy here is just 1 shot for the whole video. Proportion of saturation is the highest in the middle video here. As you can see, it's mostly saturated, all like this black colored images and all. Similarly, the lighting key here is the least because it's all dark here, whereas it's the most in this video, the first one, because it's very bright colors and very much like a beach scene and the sea here. So the lighting key is very high. So this gives you an idea what I'm talking about, right? That you extract all these type of features from the videos, and then you also have the features when I am watching these videos, how my heart is reacting, how my brain is reacting, how my facial expressions are changing. So now it is a time to combine all of these information together. So for that, we use canonical correlation analysis, CCA. So we have all these trials from these different features from the brain, from the heart, from the videos, and we use the correlation. We try to find the correlation between them. So we try to find basically the correlation between EEG and faces and the audio visual features. What we found using this was that the best features that influence your brain activity are the texture of the video, so very low level features, and the pitch of the audio. So instead of those high level features, that how the short duration is varying or if there's a voice, human voice in the video, the short the low level features, that how is the texture in the video, how are the small kind of objects that are making a texture in the video, how much are they changing from like different frames in the video. These are the features that most influence your brain activity. So this was a very crucial insight. And for the faces here, again, what we found was the features, the texture-based features. These are the features which are the most correlated with the changes in your facial expressions. And in your facial expressions, we can see the area of your nose, how this nose profile is changing. This is very crucial in all the three cases. And also the features around your how the lip height is changing, or how your eyes are opening. These are the most correlated features. So basically, we now know that these are the areas of focus, right? If you're putting a camera in front of the person and you want to know how the facial expression will change when I'm watching some content on YouTube, these are the features that are the most important. So these are the features that your algorithm should focus on. We also did the correlation between the EEG and faces directly. So in this one, again, we saw that these ones, how the eyes are opening, how the mouth is opening or closing, these are the most correlated features. And in the EEG, this beta band is the most correlated. So beta band has the most amount of information when you're watching any sort of emotional content. So if you're making a EEG system at your home, or if you are making like a EEG algorithm, you should focus more on the beta EEG band, because that's the most correlated for these type of emotions. Whereas if you are making an algorithm for facial expressions, you should focus more on detecting the changes in how the eyes are opening and lips are opening, because these are again the most correlated with your emotions. What we also did was we used deep learning here, so that we can send all of these EEG images and all of these face images into different parts, so into different layers of the deep learning network. These are the activations from each layer. And then we try to find the similarity matrix between all these different layers, like convolution 1, 2, 3, 4, 5 layers. And the highest convolution was in the middle layers here. So somewhere around here is uh, is where the EEG and the faces show the highest amount of correlation. What this means is we still don't fully understand, because what happens is in deep learning, you cannot really know what is happening in the convolution there. Deep learning is kind of a black box, but this is where we should focus on in the future, that what is happening in this convolution layer 4 and convolution layer 4 in both EG and faces. Why are we getting the highest amount of similarity in this one? We also use static and dynamic saliency. So if you have different frames here, which part of the brain is the most salient? So if you have different frames, so one by one, frame IT and the one at T+1, you can send them to the network to find, okay, this part of the brain is the most has the most amount of information in it. What we use this for is we found that these regions of the brain, as you can see, these are near the prefrontal and cortex. These regions are the brain here are most informative about low valence and high valence, whereas these regions are most informative about lower arousal and higher arousal. If we subtract these two, we find that valence is very much concentrated in this part of the brain. So this part of the brain is the part where which is like the most determinative of your mood, because as I told you earlier, valence means mood. So the difference of your mood originates mostly from this part of the brain, whereas arousal is more evenly distributed across many parts of the brain, as you can see here. So for arousal, you need activation across different parts of the brain, whereas for valence, it's more concentrated in this part of the brain. This is the part that I showed you, canonical correlation analysis just between the different modalities, but we also correlated them with the valence, arousal, and emotion as rated by the person himself or herself. So as again you see in this picture here, the correlation score changes for these different modalities, for these different pairs. So EEG and audiovisual pair, and then if audiovisual is first and EEG is later for this type of correlation canonical analysis pairs. The highest one again, as you can see here, is by this M and B, which are right height and audio features. So audio features and how the eyes are opening, and again D here, which is again an audio feature. These are most representative of how the valence and arousal is changing when you are watching a particular video content. The contributions of this part of the talk were we represented the features from two different worlds, that is multimedia content and human physiology in the same domain using CCA. So the features from how the videos itself are made and the features from the human body, they were brought together in the same world. The joint analysis provided insights into which components of the brain and which components of the faces are most informative. So now we know that how the eyes are closing or opening, how the mouth is changing the size. These are the most important features when we are trying to make a sensor in which should detect your how the emotions are changing, how the facial expressions are changing. And in EEG, we know that the beta power band is the most informative frequency band. These insights will help us in future in more effectively evoking different types of emotions in the person, because now we know for a horror video or for like exciting video or for let's say some sort of action video, what type of video will influence a person's emotion in what manner. And so we can now using these insights change the content in the video, because now we know that if we want to influence the person like this, we want to have that type of emotion in the person, you should direct the content in this type of a manner. Uh, Again, coming back to this affective states classification, the next part will talk about with how much accuracy can we predict if you are watching if you're watching like a video, if you're excited or if you are calm or if you are not aroused at all. So how good accuracy can you classify a person's state? For this, we use machine learning. So all the features that we extracted from these different modalities, we rescaled them, used a single hidden layer in ELM, extreme learning machines classifier. So this is basically just a small neural network to classify the features. What we found was we were able to beat the previous best results for all different categories, for individual modalities as well as for multi-modality. So just with using EEG or just with using ECG or GSR or using the different face algorithms, we were able to get better results for singular modalities than previously published results. But when we combine the multimodality, the results were even better. So if you use EEG and phase and you use a LSTM network over them, the accuracy increases even further and beats the previous accuracy by a lot for all these four different data sets, and also for all these parameters, valence or arousal or liking or emotions. What we also did was we were able to combine the data sets and use transfer learning, because all the algorithms that we developed, they can work even across the data set. So you can train them on like deep data set, and then you can test them on Amigos data set or Nanobatch or some other data set. So train on one data set, test on another data set. Of course, the performance will be not that great as you train on the same and test on the same, but still for all these cases it was much higher than chance accuracy. So this was the most comprehensive affective computing study in which we utilized data from different data sets comprising 122 subjects and more than 2,800 trials. The features were extracted both intuitively as well as in black box manner using the deep learning algorithms. The features proved to perform well across different data sets, and transfer learning across them was also very much robust and scalable. Finally, moving on to the last part, which was to monitor driver awareness, the second real world application. So affective computing is not just the study of human emotions or feeling, but affective computing also is a subfield Attention monitoring is also a subfield of effective computing. So attention monitoring is crucial since 1 out of 5 automobile crashes happen during falling asleep. Driver awareness has a direct correlation with how attentive the driver is. So the goal was to monitor driver's attention using different scenarios such as driving on the freeway in a narrow street, etc. Another goal was to assess driver's spatial and EEG response towards short duration hazardous events. So what we did was we used a driving simulator here. We did not perform all this when the person was actually driving. We performed this in a simulator. We have 14 channel EG, PPG, GSR, and video camera. So a person here is sitting on a driving simulator. The person has a band on the wrist, on the arm here, which measures your PPG and GSR, so your heart activity and your skin conductance. We have the person also wears a EEG headset for classifying the brain activity, for recording the brain activity here. There's a camera here facing the person to record the person's facial expressions, and the screen is here, which shows different types of like driving content so that the person is on a simulator and can react accordingly. We used 15 videos from the publicly available Kitty dataset and 20 videos which we calculated ourselves using a Tesla. Kitty dataset was used to compare the performance with existing research papers. So we ourselves, the A here are the some of the example images from the videos that we collected ourselves driving in San Diego. As you can see, there are all these different type of cases in which you're driving on a street versus when you're driving on a highway versus a good illumination, but sometimes also when you're passing under a bridge, very bad illumination. So different types of cases, sometimes pedestrians are crossing. These images are from the Kitty dataset, which has been collected by people in Germany. So again, very much different illumination, very dark here versus very light here. This is sort of like more like a highway versus this is a very narrow street. So very diverse type of videos. What we were able to show was using the different modalities and using the algorithms that I showed you, we were able to get very much high accuracy for single modality cases, as well as when we were combining the different modalities together. Uh, these were able to beat the previous best results in this case by a lot, as you can see here. And what we also did was, in addition to this only attention classification, that if your attention is low or high in for a particular video, what we also did was we also did hazardous events classification. So we took out 2 seconds events from some of these and labeled them as hazardous and non-hazardous to classify them. Now, hazardous events are kind of like when you are driving and suddenly pedestrians start crossing the road, or you are driving in this kind of very poor illumination, or someone is suddenly trying to tailgate you. Whereas non-hazardous events are like if the traffic light changed from red to green, or if there's like a crossing here, like a zebra crossing, but nobody's crossing at that time, or there's some road construction signs here. So these type of hazardous and non-hazardous 2 seconds events were marked, and again for these events we get very good classification results. The best we performed were about 95% accuracy to classify these hazardous and non-hazardous events. We had also been collecting some novel driving and multimedia data sets. So this is how a Tesla looks like from inside. It has a very big screen here. So if you are watching news in autopilot mode, uh, so for example, you're driving a Tesla, but you're not driving it yourself. You are driving it in autopilot mode. So the Tesla is driving itself and you are just busy in watching a news here. So sometimes what happens is in Tesla, it gives you a beeping sound and it asks you to take over because it cannot handle that situation itself. So you're watching news and the Tesla will suddenly start beeping and then it will ask you to take over. So here was the beep and suddenly you have to take over and you have to start driving yourself. Again, we did not do this in while we were actually driving, but we only did this in a driving simulator to kind of simulate what Tesla does when you're actually. And these type of different this is the plot of effective states versus takeover complexity. So after every such takeover, the person rates how easy or how hard was it to take over. So these are just preliminary results to show that just based on how your brain activity was, or how your pupillometry or gaze was changing, how your pupil diameter was changing, we might be able to know in future that how ready were you to take over. If the car which is driving itself like an automated car, how ready are you to take over if it asks you to take over, if it cannot handle a situation. So the contributions of this part of the talk, it was evaluated the modalities with low temporal resolution, such as PPG and GSR, but very good, but are very easily variable, or can perform as good as EEG and computer vision. So the answer was no. EEG and computer vision, though they are a little bit harder to use, because for EEG you have to put a whole headset on your head, and for vision you have to put a camera in front of you. They work much better than PPG and GSR, because PPG and GSR heart activity and skin context, and they are very low temporal resolution. The efficacy of the fusion of features for different modalities was evaluated for both this attention monitoring as well as hazard analysis. These insights will enable the design of safer automobiles, and also being able to integrate these with your smartwatches, etc. So, for example, uh, how about if your smartwatch, like your Apple Watch, it can get integrated with your car, like your Tesla car, and all the time as you are driving, your watch is monitoring if you're awake, if you're active or not, and that information is being communicated constantly with your car. That's what we talked about, 5 Ws and 1H. And again, we talked about these three parts of the three goals. So detect and monitor effective states, how to infer effective states using minimal number and most comfortable sensors. Since we used all these different sensors, now we know that for these different tasks, how much accuracy is being provided by what type of sensor, and we can infer the context in real world scenarios for all of these based on how the multimedia content is changing, how your facial expressions and brain activity is changing when that multimedia content is changing. So those were the three goals as I highlighted at the start of my talk. These will all, of course, all lead to the last two goals, that based on all this information, what recommendations should you make to the person in real time, and to be able to do this continuously throughout the day. So all of the studies that I showed you were not done throughout the day continuously, of course. That should be like the overarching goal at some point in the future, to be able to do this continuously throughout the day. In conclusion, effective computing encompasses the development of systems that can work in a multitude of challenging conditions, since human effects are highly subjective. Multimodal biosensing systems are our best bet for now, since no single modality can efficiently capture human effects continuously in the real world scenarios. As I showed you, the accuracy of these different systems, the accuracy gets better if you put multimodal systems together. If you are using a single system, like just a face expression based system, or a single brain activity system, you will face different issues, for example, of illumination or different types of noise. So you will have to use multimodality. You will have to use different systems together. However, it is never possible to include all the systems together, right? You will have to at some point make a trade-off, because you have to have the system to be compact and wearable. You cannot just ask the person to wear like 5 different sensors. So you have to find, for a particular application, what's the trade-off, what type of system should be most comfortable and compact for a particular type of application. And the hardware and software frameworks that were developed in this work, they are modular, scalable, and robust. So you can actually not just use them for emotions, but you can use them for other type of applications too. For example, if you're working on speech, or if you're working on some other computer vision based applications, all the hardware and software frameworks that we develop, they are scalable for other applications too. These were some publications in different journals and conferences that came out of this work. I would like to thank here my PhD mentors, here in the bottom left, other collaborators and the 3 labs that predominantly work, where I work predominantly for this SWAT Center for Computational Neuroscience, Facebook Reality Labs, and Laboratory for Intelligent and Safe Automobiles. At the bottom here are the different funding agencies. So many thanks to them for funding my research during my doctoral studies. Thank you.
Thank you, Dr. Siddharth. Any questions from the participants? 1 or 2 questions are allowed. If not now, I think Dr. Siddharth will share his email ID and we can share it along with our participants and they can post the questions later to Dr. Siddharth.
Yeah, sure, I'll just write it here. So it's siddharth@ucsd.edu. I hope you can all see it.
Yes. Okay, if there are no questions, let me thank Dr. Siddharth for this wonderful session. And I think this is the first session that I've heard where a lot of concepts, aspects, analysis were covered in a single session. Like Dr. Siddharth started from his how to usage of EEG, PPG, the heart activity, brain activity, combining the multimodal data with novel driving data, etc., and a lot of analysis were also being delivered, such as multimodal data analysis, canonical correlation analysis, and so on and so forth. However, the correlation with emotions were discussed in this session, but one appreciable factor here is I did not see any variation in Dr. Siddharth's tone or voice or in the content delivery mechanism. He was so cool, calm and composed in his delivery, and just his experience were been spoken up in his talk. We highly appreciate your talk, Dr. Siddharth, and we expect your cooperation in our future days for our student projects or research projects hereafter. Doctor,
Sure.
Thank you, Dr. Siddharth.
Thank you, Professor. Yeah, I would be happy to collaborate in any manner. Thank you. I'm surprised there were no questions today.
Yes, Dr. Geeta, please.
Thank you, madam. Thank you, Dr. Siddharth. It was a very informative and interesting session, and lot of research problems came out that the faculty can go ahead with it and guide their students to the research scholars also. Thank you so much for the acceptance and a very good presentation from your side. Thank you so much, Siddharth.
Thank you, Professor. I would just like to highlight again at the end here that all the research that I did, this can literally be done in any research lab in India or anywhere, because mostly all of it just requires good computers and GPUs and data sets, nothing like too fancy or too costly.
Yeah, true.
Okay. Thank you. Thank you, Dr. Siddharth.
And for the participants, we shall again get back and join at 11:30 a.m. Okay, we'll have a session from Ravindra Hegadi at 11:30. Thank you. See you at 11:30.